Module 5, Lecture A, Elementary Sorts. By the end of this lecture, you will be able to implement selection, insertion, and bubble sort algorithms in Python, analyze the time and space complexity of elementary sorting algorithms, and explain scenarios where simple sorts may still be acceptable choices. Selection sort basics. Finding minimum elements. To understand selection sort, focus on how it finds the minimum element in part of a list. Imagine scanning exam papers on a desk to find the lowest score without moving any of them. In the algorithm, you start at the beginning of the unsorted list, assume the first number is the smallest, and then compare it with each following number. By the end of this scan, you have identified the position of the smallest value without actually rearranging any data yet. Finding the minimum in a list is a systematic search where you keep track of the smallest value seen so far. As you scan through each element, you compare it to your current minimum. If you encounter a smaller value, you update your record of which position holds the minimum. By the time you reach the end of the list, this process guarantees you have identified the smallest element. Selection sort builds on the idea of finding the minimum element in a list. The algorithm repeatedly scans the unsorted portion, each time locating the smallest value and moving it to its correct position at the front. On each pass, it starts with a tentative minimum, compares it with the remaining elements, and updates which one is smallest. By repeating this pattern, it gradually orders the entire list from smallest to largest. Python code. Finding minimum elements. We want to scan a list to find the index of its smallest element and show how the current minimum index changes as we move through the list. This process illustrates how we repeatedly compare elements and update the position of the smallest value found so far. It directly connects to the minimum search step in selection sort, where we look for the smallest remaining element before swapping. For this simple script, no additional installation commands are needed. We begin with a list of exam scores expressed as percentages, arranged in no particular order. This list serves as our dataset for demonstrating how to locate the smallest value. By working with these unsorted scores, we can illustrate the basic idea of scanning through a collection to find its minimum element. We start by setting the starting index of the unsorted part of the list to 0, which means we initially treat the entire list as unsorted from the first element onward. This setup is important for algorithms like selection sort. In selection sort, we repeatedly look for the minimum element in the unsorted section and move it to the front, gradually building up the sorted portion of the list. To begin, we assume that the first element in the unsorted part of the list is the smallest and set the minimum index to that starting position. This gives us a clear reference point as we scan the rest of the list. As we compare each element to our current minimum, we update the minimum index whenever we find a smaller value. In this way, we efficiently track the position of the smallest element while iterating through the list. We begin by displaying the original list of scores so we can clearly see the data before any processing. This initial view makes it easier to follow what changes as we work with the list. In particular, it helps us understand how the values shift when we search for and identify the minimum element in the list. The program first prints a message to tell the user it is about to scan the list to find the minimum score and its index. This message prepares the user for the next step in the process. It signals that the upcoming loop will compare list elements to identify which value is the smallest. In short, it introduces the search for the minimum value and where it appears in the list. We scan through the list, starting just after the initial index, and continue until the end, looking for any element smaller than the current minimum. As we compare each element, we update our minimum candidate whenever we find a smaller value. This process lets us efficiently determine the smallest value and its position in the list. Finding this minimum is a key step in sorting methods such as selection sort. The code compares the current score in the list with the score at the current minimum index. If the current score is smaller, it updates the minimum index to this new position. By repeating this check for each score as the loop runs, the code gradually tracks and identifies the smallest score in the entire list. During the loop, whenever a smaller value is found, the code updates the stored index of the current minimum. This means the position of the smallest value seen so far is replaced with the position of this new, smaller element. By repeatedly doing this for each item in the list, the final index at the end of the loop points to the smallest value in the entire list. The code prints three things at each step: the current index, the value at that index, and the index of the best minimum found so far. This output shows how the algorithm checks each element in the list to see if it is smaller than the current minimum. By watching these values change, you can see exactly when and how the minimum index is updated during the scan through the list. After the loop finishes scanning the list, the program prints the smallest score it found and the index where that score appears. This final output clearly reports the minimum value and its position in the list. It summarizes the result of the search by confirming which score is lowest and exactly where it is located. This script finds the position of the smallest exam score in a list. It starts by assuming the first score is the minimum, then scans through the list comparing each score to the current minimum. Whenever it finds a smaller score, it updates the index of the minimum. Along the way, it reports the current position, the score there, and the current minimum index. At the end, it outputs the smallest score and where it appears in the list. Using the same idea as the minimum search step in selection sort. In-place swaps. Selection sort works directly within the original list without creating a separate sorted list. At each step, it finds the smallest element in the unsorted portion and swaps it with the element at the front of that portion. In Python, this means exchanging the values at two positions so the minimum moves forward and the displaced value takes its place. Because it rearranges elements only by swapping within the same list, selection sort is considered an in-place algorithm. In selection sort, understanding the swap step is essential because it is what actually reorders the elements. After the smallest element in the unsorted part of the list is found, it is swapped with the element at the boundary between the sorted and unsorted sections. Conceptually, this swap uses a temporary holding place for one value, moves the second value into the first position, and then moves the held value into the second position. Even though a language like Python can express this in a single line, it is still a three-step process that uses only a tiny amount of extra space, showing that selection sort simply rearranges existing elements without increasing memory usage. In-place swaps in selection sort are important when working with large datasets or limited memory because they only need a small, fixed amount of extra space. This makes them useful when you cannot afford to duplicate the data, such as when reordering records on a memory-constrained device. However, every swap directly changes the original list, so any part of the program using that list will see the updates immediately. Understanding this behavior helps you apply similar in-place techniques in other algorithms that rearrange data within existing structures. Python code. In-place swaps. In this example, we focus on how selection sort performs in-place swaps on a small list. We show how two positions in the list exchange their values using a temporary variable to hold one value during the swap. This emphasizes that the original list is modified directly in memory rather than creating a new list. No additional installation commands are needed because the script relies only on Python's built-in features. A swap-in-place function exchanges two elements in a list by using a temporary storage location. It first saves the value at the first index so it is not lost. Then, it copies the value from the second index into the first index. Finally, it moves the temporarily stored value into the second index. After these steps, the two elements have successfully traded positions within the list. The function works by moving through the list one position at a time, deciding where the next smallest value should go. At each position, it first assumes the current element is the smallest in the remaining unsorted part and marks its index as the minimum. It then scans the rest of the list to find the true smallest value. If it finds a smaller value, it updates the minimum index to that new position, preparing to place the smallest value in the correct spot. At this step in the sorting process, we swap the element at the current position with the element that has the smallest value found so far. A helper function performs this in-place swap, directly exchanging the two elements in the list. As a result, the smallest value discovered is moved into its correct position. Because the list is modified directly in memory, this approach helps keep the sorting process efficient. We begin by creating a list of numbers that represent the weights of boxes in pounds, and this list is not sorted at first. We then display this original list on the screen so we can clearly see the initial order of the weights. This gives us a reference point to compare against after we apply any sorting operations. We use selection sort to arrange the list, and this algorithm works by swapping elements directly within the original list. Because of this, the list is modified in place rather than creating a separate sorted copy. After the sorting is complete, we print the list to show that its contents have been reordered and that these changes occurred directly in memory. This script shows how selection sort can rearrange a list of weights directly in memory. It first prints the unsorted list, then repeatedly finds the smallest remaining value and swaps it into the current position using a helper function. That helper temporarily stores one value, exchanges the two elements, and updates the original list without creating a new one. After the algorithm finishes, the script prints the now sorted list in ascending order, highlighting the efficiency of in-place swaps. Efficiency and stability. Selection sort becomes less efficient as the input size grows because it repeatedly scans the unsorted portion of the list to find the smallest element and swap it into place. The number of comparisons increases with the square of the list size, so doubling the number of items can roughly quadruple the running time, and increasing the list size by 10 can make the time about 100 times longer. This quadratic growth makes selection sort slow for large datasets, but it can still be acceptable for small lists where more complex algorithms are unnecessary. Selection sort is efficient in terms of swaps because it performs only one swap per pass, even though it makes many comparisons. As a result, the number of swaps grows only linearly with the size of the list. This can be useful when swaps are expensive, such as writing to slow storage or updating large objects. For example, when sorting large multimedia files on an external drive, reducing write operations can matter more than minimizing comparisons. Making selection sort a reasonable choice despite its slower overall speed. In sorting algorithms, stability means that items with equal keys keep their original relative order, which can matter when that order carries important information such as customer records sorted by last name while preserving purchase order. Selection sort is not stable by default because swapping the smallest element can change the order of equal elements. It is possible to modify selection sort to make it stable, but this usually adds extra complexity or memory usage. Therefore, when choosing selection sort, you should consider how important stability is for your specific task. Python code, efficiency and stability. Explain selection sort by walking through its comparisons and swaps, emphasizing that the number of comparisons grows quadratically with the input size, while the number of swaps grows only linearly. Highlight that this makes selection sort relatively efficient in terms of swaps, but still slow overall because of the many comparisons. Finally, show that selection sort is not stable by demonstrating how records with equal grades can change their original order after sorting. The comment saying that no additional installation is required is simply a placeholder indicating that the code runs with the standard Python setup. It tells the user that all needed tools are already included in a typical Python environment. This helps clarify that no extra libraries or packages must be installed. As a result, anyone can run the script without performing any additional setup steps. We define a selection sort function that also counts how many comparisons and swaps it performs. At the start of the function, we set two counters to 0, one for comparisons and one for swaps, so we can track the sorting work. We then make a shallow copy of the input list, so the original data is not changed while the copied list is being sorted. In this selection sort process, we move through the array position by position, each time choosing where to place the next smallest element. For the current position, we first assume it holds the minimum and record its index. Then an inner loop scans the remaining unsorted elements, counting each comparison and updating the minimum index whenever a smaller element is found. After the scan, if the minimum index has changed, we swap the element at the current position with this new minimum and increase the swap count. We repeat this procedure until all positions have been processed and the array is fully sorted. This function returns three pieces of information: the sorted array, the total number of comparisons, and the total number of swaps. Together, these values summarize how the selection sort algorithm behaved on a given dataset. They let us evaluate its efficiency in terms of computational cost and also examine how it treats elements with equal keys. In this way, we can analyze both the performance and the stability of the sorting process. We create a list of records where each record stores a student's grade, name, and purchase order number. The records are Alice with a grade of 90 and order 1, Bob with 85 and order 2, Carol with 90 and order 3, and Dave with 85 and order 4. This setup is used to show how selection sort works when some students have the same grade. In particular, it lets us observe what happens to the original order of records that share equal grades during the sorting process. We use a selection sort function to order a list of records by their grades. As it sorts, the function also counts how many comparisons and swaps it performs. When we call this function, it returns both the sorted list and these counts. This lets us see not only the final order of the records, but also how many operations the sort needed, which helps us understand its efficiency and behavior. The code reports how many comparisons and swaps are performed by the selection sort algorithm. The comparison count shows how often elements are checked against each other to find the minimum value. The swap count shows how many times elements are actually moved to build the sorted list. Together, these numbers give a sense of how efficient selection sort is in terms of the operations it performs. We begin by printing the records in their original order, where they are sorted first by grade and then by time of purchase. This initial display is important because it lets us later compare the starting arrangement with the result after sorting. By checking whether records that share the same grade stay in the same relative order, we can determine if the sorting algorithm is stable. In other words, this step helps us see whether equal grade records keep their original sequence after sorting. We now print the sorted records to see how selection sort has ordered them first by grade and then by time. By examining this output, we can check whether records with the same grade still appear in their original order of insertion. If they do not, it reveals instability in the sorting process. This observation is important for understanding how the algorithm treats elements that share equal key values. This script illustrates how selection sort works by sorting a list of records based on grades and tracking its efficiency and stability. It counts how many comparisons and swaps occur, showing that comparisons grow roughly with the square of the list size, while swaps increase only in proportion to the list size. The original data includes records with the same grade, but different purchase orders, and after sorting, their relative order may change. This change in the sequence of equal grade records demonstrates that selection sort is not a stable sorting algorithm. The script reports the total comparisons and swaps along with the original and sorted orders to make these effects clear. Insertion sort efficiency, growing the sorted prefix. Insertion sort works by gradually building a sorted portion at the beginning of the list, starting with the first element. each new element is inserted into its correct position within this already sorted section. To do this, the algorithm may need to compare the new element with several earlier elements and shift them to make space. As the sorted section grows, the number of comparisons and shifts for each new element can increase, which is why the overall time complexity grows with the size of the list. Insertion sort is like sorting a growing hand of playing cards. You begin with one card that is already in order. Then, for each new card, you scan through the cards in your hand from right to left to find its correct position. At first, this is fast because there are only a few cards to compare. As the hand grows, each new card may require many comparisons and shifts. Because the work needed for each insertion increases with the size of the sorted part, the total running time of insertion sort grows quadratically with the number of elements. Insertion sort's running time depends heavily on the initial order of the data, because it repeatedly grows a sorted prefix of the list. With random input, new elements are usually inserted somewhere in the middle of this prefix, leading to many comparisons and shifts. With reverse sorted input, each new element must move all the way to the front, which maximizes the work. With already sorted input, each element is added at or near the end, so very little work is needed. Overall, the total cost comes from how much effort is required to extend the sorted prefix until the entire list is ordered. Python code, growing the sorted prefix. Insertion sort works by growing a sorted prefix of the array one element at a time. At each step, it takes the next element and compares it to the elements in the sorted prefix, shifting larger ones until it finds the correct position. You can think of the prefix size increasing by 1 with each insertion, while the number of comparisons for that step depends on how far the new element must move. Over the whole array, these repeated comparisons and shifts add up, leading to a total running time that grows roughly with the square of the number of elements. The commented line is suggesting the installation of Matplotlib, Seaborn, and NumPy using a package manager, which is common when setting up a Python environment outside of platforms where these libraries come pre-installed. These tools are mainly used for data visualization and numerical calculations, such as analyzing or plotting the results of algorithms like insertion sort. However, because the line is commented out, it indicates that you do not need to run this installation step if your environment already has these libraries available. We define a version of insertion sort that also tracks how the sorted part of the list grows. Inside this function, we create a list to record what happens at each step of the sort. We then move through the list starting from the second element, treating the first element as already sorted. For each new element, we save its value, set a position index to the element just before it, and start a counter for comparisons. This setup lets us measure how many comparisons are needed to place each element into its correct position within the sorted portion of the list. In this loop, we repeatedly check whether the current index is still within the list and whether the element at that index is larger than the value we want to insert. If both conditions hold, we count this as a comparison and then shift that larger element one position to the right to make room. After shifting, we move the index one step backward to examine the previous element in the sorted portion. This process continues until we reach an element that is not larger than the value being inserted, or we run out of elements to check, ensuring the sorted order is maintained. After the while loop finishes, the code checks whether the position index is still 0 or positive. If it is, that means the current value was compared with the element at that position before the loop ended. In this case, the comparison counter is increased by 1 to include that final check. This ensures that every comparison made during the search for the correct position of the current value is accurately counted. At this step, the current value is reinserted into the list at its correct position, so the sorted order is preserved. The size of the sorted prefix is then updated to be one more than the current index, indicating how much of the list is now sorted. Information about this step, including the prefix size and how many comparisons were needed, is stored for later analysis. This function returns two results: the list after it has been sorted and a record of what happened at each step of the sorting process. The sorted list is simply the original list rearranged into order. The step details describe how large the sorted portion of the list is at each stage and how many comparisons were needed. Together, these details show how the sorted part of the list grows with each insertion and give insight into how the algorithm works and how efficient it is. We begin with a small unsorted list of numbers: 9, 3, 7, 1, 5, and 2. This compact list is chosen so the sorting process stays clear and easy to follow. It will serve as the input to the insertion sort algorithm, allowing us to observe how the algorithm rearranges these values into sorted order step by step. We run the insertion sort function on a copy of the unsorted list, so the original data is not changed. This function returns the completely sorted list, along with a record of how the sorted portion grows at each step. For every insertion, it tracks the size of the sorted prefix and how many comparisons were needed. Using this information, we can analyze how efficiently the algorithm works and how it gradually builds the sorted list. The code first prints a header line that explains the structure of the data that will be shown next. It labels the columns as the current step, the size of the sorted prefix, the number of comparisons made in that step, and the total number of comparisons so far. This header creates a clear format for tracking how the sorted portion of the list grows during the insertion sort process. We keep track of how many comparisons have been made in total as the sorted prefix grows. For each step, we look at the current prefix size and the number of comparisons used in that step, then add that number to the running total. At each stage, we report the step number, the prefix size, the comparisons made in that step, and the cumulative comparisons so far. This process shows how the total number of comparisons builds up as the prefix becomes larger. The code prints a final message to indicate that the insertion sort process is complete. It then displays the fully sorted list after the sorted portion has been expanded step by step. This output lets you clearly see the end result of the algorithm and confirms that the list has been completely sorted through its iterative procedure. This script illustrates how insertion sort gradually builds a sorted prefix of a list and tracks the work it does. Starting from an unsorted list, it inserts each new element into the correct position in the growing sorted portion and counts how many comparisons are needed. At each step, it reports the current size of the sorted prefix, the comparisons used for that insertion, and the running total of comparisons. By the end, you see the fully sorted list and how the increasing number of comparisons reveals the quadratic time complexity of insertion sort. Efficient element shifts. Insertion sort works by shifting elements to make room for the current value, rather than repeatedly swapping pairs like bubble sort. You can think of it as sliding items over to open a gap for the new item. Each individual shift is quick, but the total work depends on how many elements are out of place. In the worst case, when each new element is smaller than all the ones already sorted, the entire sorted portion must move right each time, leading to many small but cumulative moves. Insertion sort is mainly costly because it must shift elements to make room for each new value. At each step, it compares the current value with the already sorted part and moves larger elements to the right. If the data is in reverse order, many elements must be shifted, making it slow, but if the data is already sorted, new elements are simply added at the end with minimal work. This sensitivity to how far elements need to travel explains why insertion sort can be efficient in some situations and inefficient in others, even though the algorithm itself does not change. Insertion sort works directly within a single block of memory, shifting elements in place without extra data structures, which fits well with how modern memory systems operate. This leads to efficient, localized memory access, making it surprisingly fast for small or nearly sorted datasets, even though its theoretical performance is poor on large, random data. A common example is inserting a new row into an already sorted spreadsheet, where only a few nearby entries need to move. Because of this practical efficiency on small segments, insertion-style techniques are often used inside more advanced sorting algorithms. Python code. Efficient element shifts. We will illustrate how insertion sort works by showing, step by step, how elements are shifted into their correct positions. As we do this, we will compare the cost of shifting elements with the cost of swapping them, so you can better understand how much movement the algorithm performs. We will also examine how many shifts are required for different input orders, such as nearly sorted or completely unsorted data. If needed, you can install any required library beforehand to support these demonstrations. We define an insertion sort function that also counts how many element shifts occur during sorting. To avoid changing the original data, we first work on a copy of the input list. We then set up a counter that increases each time an element is moved to a new position. This shift count lets us measure the movement cost of the insertion sort process. In this step of the algorithm, we move through the list, starting from the second element, since the first element is already treated as sorted. For each new element, we store its value as the current item we want to insert into the correct position. We then set a comparison index to the position just before this item. Using this index, we compare the current item with elements in the sorted portion of the list to find where it should be inserted. In this step of the algorithm, we repeatedly compare the current element with the key we want to insert, as long as the index is not negative and the element is larger than the key. Whenever the current element is larger, we move it one position to the right to make room for the key. Each time we move an element, we increase a counter that tracks how many shifts have occurred. After each shift, we move the index one position to the left and continue this process until we find the correct place to insert the key. This step places the current key into its correct spot within the already sorted part of the list. After any larger elements have been shifted to the right to make room, the key is inserted at the proper index. This ensures that up to this position, the list remains correctly sorted. The function finishes by returning two results: the list in its sorted form and the total number of shifts made during sorting. The sorted list shows the final order of the elements, while the shift count indicates how many element movements were required. Together, these outputs provide both the outcome of the sorting and a simple measure of the computational effort involved. The run scenario function carries out a sorting task and reports its outcome. It first calls the insertion sort with shifts function on a list of values, which returns the sorted list and the number of shifts made during sorting. The function then prints the scenario name and the original list to show what is being sorted. After that, it prints the sorted list and the total number of shifts, giving a sense of how the algorithm performed for that scenario. We will use three small lists of numbers to see how insertion sort behaves in different situations. One list is nearly sorted, with only the last two elements out of place, to show how the algorithm handles a small disruption. A second list is in reverse order, which forces the algorithm to make the maximum number of shifts. The third list is in random order, representing a typical unsorted case. By comparing how many shifts insertion sort performs on each list, we can see how the initial order of data affects its work. We test insertion sort under three different starting conditions to see how many shifts it performs. First, we use a list that is nearly sorted to observe how few shifts are needed when the data is close to ordered. Then, we sort a list in completely reverse order, which shows the maximum number of shifts because every element must move. Finally, we sort a randomly ordered list to see a more typical shift count. Comparing these scenarios reveals how the initial arrangement of data affects the efficiency of insertion sort. This script illustrates how insertion sort works by counting how many element shifts it needs to sort different types of lists. It tests nearly sorted, reverse ordered, and randomly ordered lists, and for each one, it shows the starting list, the sorted result, and the total number of shifts. The nearly sorted list needs only a few shifts, while the reverse-ordered list needs the most. This comparison highlights how the cost of moving elements in insertion sort depends strongly on how ordered the data is to begin with. Nearly sorted performance. Insertion sort works especially well when the data is already close to sorted because it adapts to the existing order. Instead of following a rigid pattern, it looks for elements that are out of place and moves them to where they belong. In nearly sorted lists, each new element is usually very close to its correct position, so only a few comparisons and shifts are needed. As a result, the total work grows mainly with the number of small corrections required, rather than with the square of the list size seen in its worst cases. Insertion sort works especially well when a list is already almost in order. In that case, most items are quickly checked and confirmed to be in the right place. Only the few out-of-order items, called inversions, need to be moved a short distance. Because there are so few of these inversions, the algorithm does much less work than it would on a completely disorganized list. Insertion sort is especially efficient in real-world systems where data changes gradually, such as updating scores or adding new entries to a mostly ordered list. When the data is already close to sorted, it can run in nearly linear time and uses very little extra memory. This makes it well-suited for refining an almost sorted list or keeping data in order when there are frequent small updates. As a result, insertion sort is often used as a final pass or maintenance tool in dynamic environments where order is mostly preserved. Python code, nearly sorted performance. We want to compare how fast insertion sort runs on nearly sorted lists versus completely random lists. Instead of measuring actual running time, we will count how many operations the algorithm performs in each case. This helps show that when the input is already close to sorted, insertion sort needs far fewer operations. As a result, nearly sorted inputs make insertion sort behave almost like a linear time algorithm, while random inputs require much more work. This line indicates that you do not need to run any pip install commands because the script uses only Python's standard library. All the features it relies on are already included with a normal Python installation. As a result, there are no external packages or extra setup steps required. This makes the code easier to run in any standard Python environment without worrying about additional dependencies. We define an insertion sort function that also tracks how many comparisons and shifts occur during sorting. Two counters, one for comparisons and one for shifts, start at 0. The algorithm processes the list from the second element onward, temporarily storing each element and moving larger elements one position to the right while counting each comparison and shift. When the correct spot is found, the element is inserted, and if the final comparison is valid, the comparison counter is updated again. After all elements are processed, the function returns the total number of comparisons and shifts performed. We begin with a list of numbers that is almost completely sorted, except for two elements that have been swapped. This small disruption creates a nearly ordered sequence. Using this list, we can observe how insertion sort behaves when the data is already close to sorted. This setup helps demonstrate that insertion sort is especially efficient in such near-sorted situations. We create a completely random list of numbers that contains the same elements as the nearly sorted list, but in a shuffled order. This random list lets us see how insertion sort behaves when there is no initial order in the data. By comparing its performance on the random list to its performance on the nearly sorted list, we can highlight how efficient the algorithm is with different types of input. We first create copies of both the nearly sorted list and the random list, so the original data is not changed by the sorting process. Sorting usually modifies a list in place, so working on copies protects the original versions. This lets us compare the lists before and after sorting and ensures that any performance comparison between the two types of data is fair and consistent. We begin by running the insertion sort algorithm on a copy of the nearly sorted list. As it runs, we record how many comparisons and how many shifts it performs. These two counts show how efficient insertion sort is for this type of list. We store these results so we can later compare them with the counts we get when sorting a random list. We now apply the insertion sort algorithm to a copy of the random list. The sorting function reports how many comparisons and how many shifts it performs while sorting. We record these counts as the number of comparisons and the number of shifts for the random list. By doing this, we can see how insertion sort behaves on a completely unsorted list by measuring how many operations it needs to put the data in order. We begin by printing a summary of the sorting results for both lists. For the nearly sorted list, we show how many comparisons and shifts insertion sort performs, highlighting its efficiency when the data is almost in order. We then display the same counts for the random list to contrast how much more work is required when the data is unordered. Finally, we print the original versions of both lists to confirm that sorting was done on copies and the original data was not changed. This script compares how efficiently insertion sort works on a nearly sorted list versus a completely random list by counting the number of comparisons and shifts instead of measuring time. It uses a version of insertion sort that tracks these operations, then applies it to one list that is almost in order and another that is fully jumbled. The results show that the nearly sorted list needs far fewer comparisons and shifts, demonstrating that insertion sort runs in almost linear time when the data is already close to sorted. The original lists are also printed to confirm they are not modified by the counting process. Bubble sort basics. Adjacent swaps explained. This sorting method works by repeatedly comparing and swapping only neighboring items. You move along the list from one end, and whenever two adjacent values are out of order, you swap them. As you do this, larger values gradually move toward one side of the list, much like heavier objects settling at the bottom when a container is shaken. Because it relies only on local, step-by-step exchanges and never on long jumps, the method is simple and intuitive to understand. This method works by comparing and possibly swapping only neighboring elements, which makes it simple to understand and implement. You can think of it like lining people up by height and swapping two neighbors whenever the taller one is in front, so that after several passes, the tallest person ends up at the back. Although this approach is not very fast for long lists, it is intuitive and effective for small sets of items, or when you only need a quick, approximate ordering. Adjacent swaps are useful for fixing small, local disorder in a list that is already almost sorted. When only a few elements are out of place, nearby exchanges can quickly restore the correct order. This approach is efficient in digital systems where moving data over long distances is expensive, so it works well for small collections or data that is nearly in order. Python code. Adjacent swaps explained. Use simple height values in inches to demonstrate how bubble sort works through adjacent swaps. During a single forward pass, compare each pair of neighboring heights and swap them if the left one is taller. By repeating these local neighbor comparisons across the list, the taller values gradually move to the right. This shows how bubble sort relies only on local exchanges to push larger elements toward the end of the list. This script does not require any pip install commands because it uses only Python's built-in standard library. By avoiding external packages, the code is simpler to run and does not need extra setup. This also makes it more likely to work consistently across different systems and environments. We begin with a list of numbers that represent the student's heights in inches. This list is simply an array where each value corresponds to one student's height. We then display the list to show the original order of the heights. This initial output serves as a reference point for comparing how the list changes after any sorting or swapping operations are applied. We now perform a single pass of the bubble sort algorithm from left to right. In this pass, we compare each pair of neighboring elements and swap them if they are in the wrong order. By doing this across the list, larger elements are gradually pushed toward the end. This repeated movement of larger values toward the right creates the bubbling effect that gives bubble sort its name. We go through the list of heights by looking at each pair of neighboring elements, starting from the first and stopping at the second to last. In each step, we treat the current element as the left value and the next element as the right value. This lets us compare every neighboring pair in the list. Using these comparisons, we can decide whether each pair needs to be swapped to help sort the list. This code prints a message showing which two neighboring values in the list are being compared during bubble sort. By displaying each pair of heights under consideration for a swap, it lets you follow the algorithm's progress through the list. This gives a clear, step-by-step view of how the sorting process works and how the order of the values changes over time. When the left neighbor is taller than the right, we swap their values so the taller one moves to the right and the order is corrected. To do this, we temporarily store the left value, copy the right value into the left position, and then place the stored value into the right position. This simple swap operation ensures that taller values shift rightward and helps maintain the proper ordering. When a swap happens, the program prints a message and then shows the updated list of heights so you can see how the order has changed. If no swap is needed, it prints a different message to confirm that the order stays the same. These messages help you follow the sorting process and understand whether each pair of neighboring values needed to be adjusted. After completing one pass of the bubble sort loop, we print the list of heights to show the result of that pass. This output reveals how the list has changed due to the agency swaps. It makes it easy to see how the taller values have moved toward the right side of the list. In this way, the printout clearly demonstrates the effect of the bubble sort process after a single pass. This script shows one pass of the bubble sort algorithm using a list of student heights. It first prints the original list, then moves from left to right, comparing each pair of neighboring heights. Whenever a left height is greater than the one on the right, the two values are swapped, pushing taller heights toward the end of the list. After each comparison, it reports whether a swap happened and shows the current list. At the end, it prints the updated list to illustrate how some of the taller values have started to bubble up toward the right side. Early exit optimization. Early exit optimization makes bubble sort more efficient by allowing it to stop as soon as the list is sorted. Instead of always running a fixed number of passes, the algorithm tracks whether any swaps happen during each pass. If a full pass completes with no swaps, It concludes the list is already sorted and stops immediately. This avoids unnecessary work and is especially helpful when the data is already sorted or nearly sorted. Early exit optimization in bubble sort is especially helpful when data is already mostly in order. In situations like customer support systems, where tickets are usually sorted by priority and arrival time, new entries may only slightly disturb the order, so bubble sort with early exit can quickly restore it and stop once no more swaps are needed. The same idea applies to a classroom grading system where scores are typically entered in ascending order, allowing the algorithm to confirm the list is sorted or make just a few swaps. Overall, this approach avoids unnecessary passes through the data and improves efficiency when the list is nearly sorted. Early exit optimization helps explain why simple algorithms, like bubble sort, can still be useful in certain situations. When datasets are small or already close to sorted, this optimization makes bubble sort run in almost linear time. In these cases, especially in embedded systems, quick prototypes, or educational tools, simplicity, easy debugging, and predictable behavior matter more than maximum performance. As a result, an early exit version of bubble sort can be a practical choice without the added complexity of more advanced algorithms. Python code. Early exit optimization. This section explains how bubble sort can be optimized with an early exit. It compares the standard version, which always makes the full number of passes through the list, with an improved version that stops as soon as a pass makes no swaps. Using simple list examples, you can see that when the data is already sorted or nearly sorted, the optimized bubble sort finishes in fewer passes. The main idea is that detecting no changes in a pass lets the algorithm end early and avoid unnecessary work. The script explains that you do not need to run any pip install commands because it only uses features that come built into Python. In other words, it does not depend on external libraries or packages that require separate installation. This reassures you that everything needed to run the code is already included with Python. As a result, running the script is simpler and avoids possible compatibility problems with extra packages. In the standard bubble sort algorithm, we first find the length of the list and use it to control two nested loops. The outer loop represents each pass through the list, and a counter tracks how many passes we make. The inner loop compares each pair of neighboring elements and swaps them if the earlier one is larger, gradually moving larger values toward the end. With each pass, the inner loop runs fewer times because more elements at the end are already in place. When the sorting is complete, the function returns the total number of passes, which gives a sense of how much work the algorithm performed. This description explains a bubble sort function that includes an early exit optimization. It first finds the length of the list and sets up a counter for how many passes it makes. For each pass, it assumes no swaps will occur, then compares each pair of neighboring elements and swaps them if the earlier one is larger. If any swap happens, it records that the list may still be unsorted. After each pass, it increases the pass counter, and if a full pass finishes with no swaps, it stops early because the list is already sorted. The function then returns the total number of passes it performed. We use a list of numbers from 1 to 5 that is already sorted in ascending order to show how the early exit optimization in bubble sort works. With this input, the optimized algorithm can detect during the first pass that no elements need to be swapped. Once it sees that no changes are required, it stops immediately. This demonstrates how the optimization avoids unnecessary extra passes when the data is already sorted. We create a list of numbers that is almost sorted, containing 1, 2, 4, 3, and 5, where only the 4 and 3 are out of order. This nearly sorted list is used to show how bubble sort with an early exit optimization works. Because the list is already close to sorted, the algorithm can detect that only a small amount of swapping is needed and stop early. This demonstrates that the optimized bubble sort avoids unnecessary passes when the data is already almost in order. We run the standard bubble sort on a copy of an already sorted list, so the original data is not changed. During this process, the algorithm counts how many full passes it makes before confirming that the list is sorted. This count, stored as the number of standard passes on the sorted list, shows how many iterations bubble sort still performs even when the input is already in order. It helps us understand the algorithm's behavior and efficiency in this best-case scenario. We run a bubble sort with an early exit feature on a copy of an already sorted list, so the original data stays unchanged. The algorithm makes passes through the list, checking whether any swaps are needed. If it completes a pass without making a swap, it stops immediately, which shows the list was already sorted. We record how many passes were required to demonstrate how this early exit strategy improves efficiency by avoiding unnecessary work. We first run the standard bubble sort on a copy of the nearly sorted list, so the original stays unchanged. The algorithm repeatedly compares adjacent elements and swaps them if they are out of order, making multiple passes through the list. We count how many passes it takes to fully sort the list using this basic method. This pass count is then used to compare the efficiency of the standard bubble sort with an optimized version that can exit early. We run a version of bubble sort with an early exit feature on a copy of a nearly sorted list. This version stops as soon as it completes a pass without making any swaps, which means the list is already sorted. Using a copy protects the original list, so it can still be used for other operations or comparisons. The number of passes needed to sort the list is stored in a variable, allowing us to compare how efficient this early exit version is compared with the standard bubble sort. This code measures how many passes the standard bubble sort algorithm makes when sorting a list that is already in order. It shows that even in this best case, the basic version of bubble sort still goes through all its passes. As a result, it performs unnecessary work instead of stopping early when the list is already sorted. This highlights the inefficiency of the standard bubble sort approach. We measure how many passes bubble sort needs when it uses an early exit optimization on an already sorted list. This shows that the algorithm can stop as soon as it detects that no swaps are required. Because no elements need to be moved, the early exit prevents extra passes. As a result, the sorting process is more efficient on data that is already in order. This code measures how many passes the standard bubble sort needs to finish sorting a list that is already almost in order. It does this so we can compare its efficiency with an improved bubble sort that stops early when the list becomes sorted. The result, stored as the number of passes on the nearly sorted list, is then printed to show how many full iterations the unoptimized algorithm performs. We report how many passes the bubble sort with early exit takes when it runs on a nearly sorted list. This lets us compare its efficiency to the standard bubble sort. By seeing that the optimized version stops after fewer passes, we can clearly observe how the early exit avoids unnecessary work when the list is almost sorted. This script compares standard bubble sort with a version that includes an early exit optimization. The standard algorithm always makes all its passes through the list, even if the data becomes sorted before it finishes. The optimized version stops as soon as a pass completes with no swaps, which means the list is already sorted. As a result, an already sorted list takes only one pass with the optimized version instead of 5. And a nearly sorted list takes 2 passes instead of 5. This shows how early exit can greatly reduce unnecessary work when the data is already or almost in order. Limits of bubble sort. Bubble sort is rarely used in real software because it repeatedly compares and swaps neighboring items, which creates many small operations. This approach becomes very inefficient as the amount of data grows, so the algorithm slows down a lot, even for moderately sized inputs. It may be acceptable for demonstrating sorting on a short list in a classroom, but it is impractical for sorting thousands or millions of records in real applications, such as organizing customer transactions. Bubble sort is inefficient because it cannot take full advantage of data that is already partially ordered beyond a simple early stop. It continues to perform many unnecessary comparisons and swaps even when the data has helpful patterns, such as repeated values or only a few elements out of place. As a result, it performs poorly on complex datasets like sensor readings or financial prices. This lack of adaptability means bubble sort is usually outperformed by more advanced algorithms that adjust their behavior based on the structure of the input data. Bubble sort is rarely used in modern software because it is slow and does not scale well. Large systems often need sorting algorithms that work efficiently with parallel computing, distributed data, concurrency, and memory constraints, which bubble sort's simple, sequential design cannot handle. It also cannot easily distribute work across multiple processors. As a result, even in smaller projects, developers rely on optimized library sorting functions, and bubble sort is mainly kept for educational purposes to illustrate basic sorting concepts rather than for real-world use. In this lecture, you learned to implement selection, insertion, and bubble sort algorithms in Python, analyze the time and space complexity of elementary sorting algorithms, and explain scenarios where simple sorts may still be acceptable choices. In the next lecture, Lecture B, we will go over efficient sorting. Thank you for your attention. See you all in the next lecture.